Hello and welcome to this video on graphing simple rational functions. We are going to be graphing functions that generally look like the one we're seeing in front of us. This is the parent function. Recently in class, we've been talking about inverse variation. This is basically taking an inverse variation graph you can see in the top right and graphing the entire function if we're trying to graph f of x equals 1 over x. And we're kind of seeing both sides as opposed to just inverse variation is just the top right. So the general version of this parent function would be a over x minus h plus k. And the a, h, and k are going to be causing transformations to happen to this function, just like the other families we've discussed in class, which would include square roots and quadratics. And we're going to be using the same transformational vocabulary that we used back in chapter 1 when we were transforming geometric shapes. These are also called rational functions because we have basically an expression in the top and the bottom. And you'll see much more complicated versions of these in future classes next semester. So in the graphs that we are going to be looking at, we are going to kind of remember what we've seen with a, h, and k in the past. So for a is going to cause dilations. And remember, when we are causing dilations, this is really only changing the y values, changing y values. The x values themselves are still going to be just our inputs. So if you're going to dilate at something, the x is still with the same x as before, but now we are kind of causing larger y values or smaller y values based upon having large or small a values. If we have a negative a value, that means we are going to have a vertical reflection, just like we saw with quadratics and square roots. That's going to cause it to flip upside down if it is negative. Now, if we have h and k, h is going to cause horizontal translation. And remember, when you have h, because we have an x minus h at the top, the h value you're looking at is going to be kind of going the opposite direction than what you might guess if you're looking at it. If it's x plus 2, it's moving left. If it's x minus 4, it's moving right, for instance. And then k finally is going to be vertical translation. These are easier because they are going to go the same direction that your intuition would tell you. And so this should be very familiar because this is exactly how it worked in prior families of functions. A, h, and k are basically doing the same things. We have a new vocabulary term that will be kind of simplified in our chapter right now and then expanded upon in Math 3. An asymptote is the new vocab word here. It is essentially an imaginary dotted line you could draw on a graph that your function is not going to cross, but it's going to become very, very close to when you graph it. So for example, if we're trying to graph this y equals 1 over the quantity of x minus 2 plus 4, x equals 2 would be our vertical asymptote. We can draw that with a vertical dotted line. And y equals 4 would be our horizontal asymptote. And you can see that with this horizontal line right here at y equals 4. And we know that by basically looking at, well, I would have a translation to the right 2 and up 4. So instead of our asymptotes being at the x and y axis like we saw with our inverse variation function in prior classes, well, now it's going to be moving over 2 and then up 2 and then 4 spaces. And from there, we really can just kind of sketch our curves. If it's kind of a positive, this a value is positive, we're basically just kind of sketch a curve up in the top right part and then sketch a curve kind of near the bottom left part of our graph. And that essentially is all there is to it. And we're going to ignore the x part. And so we're basically going to use h and k to identify our asymptotes, draw dotted lines to represent them on our graph. We're going to find our y-intercept by making x 0 and solving for an answer. So for instance, in this problem, our y-intercept would be found by doing 1 over 0 minus 2 plus 4, which would be negative 1/2 plus 4 equals positive 3.5, which, as you can see, that looks like where it's plotted on our graph below. And that'll also kind of tell you where one of your graphs is going to be. And then the other part is always just directly diagonal from the other kind of half of this function. And that really is as much as we need to be aware of before trying some examples. In this case, we're going to be looking at domain and range as well. And as you can see, that we would have at the ends of all of these graphs, like I basically can draw in arrows so that we could say that the function, when it starts to go left or down or up or right, is going to continue in that same direction without changing directions towards positive or negative infinity, x or y. So let's look at some examples, and you'll kind of have an idea of what I mean about domain and range, and get into that now. So example 1, we're going to be graphing the function y equals 1 over x plus 3, and then minus 6. So first and foremost, we're going to draw our asymptotes. So our h value, so we're basically going to take the opposite of this plus 3, since it's kind of x minus negative 3, and say our h is equal to negative 3. So our vertical asymptote would be at x equals negative 3. So I'm going to go to negative 3 and draw a little dotted line at negative 3 here on my x-axis, going up and down. So I have that vertical line, if you can see that on my graph. And then the same thing for k. I'm going to look at this negative 6 and say that k equals negative 6, and my horizontal asymptote is going to be at y equals negative 6. And so that means I can draw my flat line at 1, 2, 3, 4, 5, 6 spaces underneath of my x-axis. And that's where I'll draw my blue dotted horizontal asymptote. And a big part of graphing this function is already done for us right there. So we have kind of split up into 4 parts on here. And so now we can look at our y-intercept. So our y-intercept will be making x 0. So I have 1 over 0 plus 3, or 1/3, minus 6, equals negative 5.66, or negative 5 2/3. Now I could go to my y-axis and go to the point negative 5 2/3. So I have that orange point right there. And all that's left for me to do is just draw my graph kind of as a curve, kind of going close to this first asymptote and curving through this orange point. And then the other one will kind of be diagonal from it. So let's kind of draw our first part. So we have our first part in blue right there. And then our second part will kind of just look similar. And we have that second part of the graph down there at the bottom. That leads us to domain and range. For domain, we have x going left right here and x going right over here. Those are going to go to negative and positive infinity. The only number that we can't use is where this asymptote is, negative 3. The reason why we can't use it is that we have negative 3 plus 3, that would equal 0, and we would have 1 over 0, which is not okay. So our domain, we're going to write it as x is not equal to negative 3. What that means is basically that x can be any number but negative 3. And then our range, is going to end up being y is not equal to negative 6. So we can see that First, because of our asymptote, we're not going to have -6. Also, because our fraction is going to be subtracting 6. We already know there's no way for this first fraction to equal 0 because the numerator is always just a 1. 1 over anything is not going to be equal to 0. So there's no way we'd have 0 minus 6 equaling 0. So y can't ever be -6. It's always going to be something minus 6 instead. And that something is not going to be 0. So we have now finished example 1. We have our horizontal translations. We know that we moved left 3 and down 6. We draw in our horizontal asymptote at -6, our vertical one at -3, and we found our domain and range to be x is not equal to -3, and our range is y is not equal to -6. So let's move on to example 2 now, after you've kind of taken a look at what we have here. Example 2 has a lot of similar elements, but we'll have a little bit different of an approach here in some places. So for starters, we can maybe even do our y-intercept first. So our y-intercept is going to be 4 over x minus, or 0 minus 1, put a 0 in for x, plus 5. So that would be -4 plus 5 equals 1. So I have my y-intercept at that orange point of 1. Now I can look at my asymptotes. So I can see that my h value, it's x minus 1 here. So my h value is going to be the opposite and be a positive 1. So my vertical asymptote is going to be at x equals 1. So let's draw a dotted line at x equals 1. So we have that dotted line right there. Now our k value is going to be the same as that last number in our equation. It's going to be k equals 5, meaning our horizontal asymptote is going to be y equals 5. And now let's draw in our horizontal asymptote. We go 1, 2, 3, 4, 5 spaces up. So we have that horizontal asymptote. And we can draw in that fully on our graph. And we really have enough information now to draw a rough sketch of what the graph will look like. And so now we know that our first function is going to kind of be up by our horizontal asymptote and then eventually go through our y-intercept of positive 1. And then the other part of the graph is going to be in the top right corner up here. And so we can draw a rough sketch of that part as well. So if you think about this in terms of transformations, well, we know we translated 1 to the right, and we've translated 5 up. This 4 right here, that means we are dilated by 4. So what that will really change about this graph is that these parts kind of close to the center of our asymptotes right there, right here, these kind of curved parts are just going to be further away from the center if we have it dilated by 4. If that was a 1, these curved parts would be a little closer to the center is right here. But they're a little farther away because of that 4 now. So our domain of this function, our domain, now we know that our vertical asymptote was at x equals 1. So our domain is just going to be x can't equal 1. Can't divide by 0, just like before. And then our range is going to be y is not equal to our horizontal asymptote, which was 5. And that completes example number 2. Make sure you are paying close attention to how this is working out here. And we are, remember, we went through our y-intercept, both asymptotes. We mentioned our transformations, and we've also done domain and range. Let's move on to our last graphing example, which would be example number 3. So here we have another difference in our graphs, and then we have our a value is equal to -2. And so let's kind of go through the order here. So we're going to find our y-intercept first. In this case, we have -2, make x equal to 0, and evaluate this expression. Maybe -2 over -2 is 1, plus 1 equals 2. So I have my point at y equals 2 for my y-intercept. And now we can look at our h value. It's going to be the opposite of this -2, so that we have h is equal to 2, and our vertical asymptote is x equals 2. Our k value is a 1, and that means our horizontal asymptote is y equals 1. So I'm going to draw a vertical dotted line at x equals 2, and a horizontal line at y equals 1. So let's draw those in. So we have our vertical one at x equals 2, and then y equals 1. We can draw another orange dotted line at that right there. So you can see we have our horizontal one right here, and then our vertical one right there. And so we can start now drawing our graph. So we'll do that in dark blue. So in our graph here, if we draw our graph through our y-intercept, you will notice that our graph has going to be kind of the flipped over version of the one we started with. And so we have that graph right there. And you can see how it's kind of flipped upside down. So it used to be top left and then top right, or bottom left and top right, I mean. But now we have top left and bottom right because we have a vertical reflection because it's -2. So that -2 is a reflection, and it is a dilation by 2 as well. So 2 different transformations to go along with going translated right 2 and then up 1 for our graph here. Lastly, we will look at our domain and range. So our domain for this problem is going to be that x is not going to be equal to 2, and our range is that y is going to be not equal to +1. So that's all 3 of our graphing examples. Make sure you kind of take a close look at our final result here in front of us. Moving to example 4, we're kind of going backwards now, looking at transformations. So if we have our parent function, we're translating left 2 units and up 1 unit to get a new equation. That new equation would end up being 1 divided by the opposite of this 2 left. So it would be 2 units left would be x plus 2, and then 1 unit up would be a +1 on the end, and we have that equation for us. If the function y equals x increased by a scale factor of 7, gone 10 right and 3 down, that means that our new equation would give us 7 on the top, and we have x minus 10 on the bottom, and then we have 3 down, which would mean a -3 on the end. And that would be going backwards, starting with transformations to create a rational function that we could then go graph if we wanted to. So now we will end this video with a kind of practice problem of what just happened and kind of look through from start to finish what you would do. So let's kind of look through this, and I'm going to add the top here, y-intercept. And so I want you guys to take a second to try to see if you can figure out the answers to all 6 of these parts and think about what each answer would be before we go through it together. So pause the video here to give that a try. Okay, so now let's go through all 6 of these parts and then draw our graph to wrap up this video. So now our y-intercept, we have 2 over 0 minus 3 plus 2. That is going to be the same as negative 2/3 plus 2. So that would be 1 1/3, or 1.33. Our h value is going to be equal to 3. So we're going to draw a vertical asymptote at 3 for x. And then our k value is going to be equal to 2. So our horizontal asymptote is going to be y equals 2. Our domain is that x cannot be 3. We can't have that become a 0 under our fraction. 3 minus 3 would be 0. That's a bad thing. And range cannot be 2 because we basically have a fraction that can't be 0. If you have something that's not 0 and you add 2 to it, it's not going to equal 2. The only way for it to equal 2 would be if this fraction was 0, but it can't be 0. The numerator is already a 2. And finally, transformations, we could list those out here. So we would have it dilated by 2. We translate right 3 and translate up 2. And now let's finish this off by drawing a picture of our graph. So we can do our asymptotes first. So at x equals 3, we're going to draw in a vertical asymptote here. So we have that vertical asymptote drawn in there. So at x equals 3 right there. And then our y asymptote, or our horizontal asymptote, is at y equals 2. So let's draw it first. And so that's y equals 2, our horizontal asymptote. Our y-intercept was about 1.33, which would be approximately right at that light blue point right there. Only left thing for us to do is draw in our graph here. And we can draw that in orange right there in the bottom left. And so now we can draw in our orange graph in the top right. And so now we have a rational function graph for the function y equals 2 over x minus 3 plus 2. And that concludes everything you will need to know for Math 2 on graphing simple rational functions, a topic we will definitely expand upon next semester in Math 3. But otherwise, thank you for watching this video on graphing rational functions.